Now let's start with the new topic, that is power spectral density of M-PSK signal. Till now what we have seen, if this is a M-PSK transmitter, the output of this M-PSK transmitter would be root ES cos of theta m phi IT plus root ES sine of theta m phi QT, where theta m is 2m minus 1 pi by capital 1 and m varies from 1 to m, and the time duration over which this communication is taking place is from 0 to n TB, where n is log 2. Or the same signal can be seen as EC AC cos of 2 pi FCT plus theta m. Theta m is same as this and t is again from 0 to n TB. So this is the representation of the signaling basis function, and this helps us to realize the constellation diagram. This is theta 1, this is theta 2, this is theta 3, and this is theta 4. And this is root ES, because we know that this is the energy and energy is ES, therefore. And how this ES and AC are connected? Because if you remember, AC cos 2 pi FCT, the energy of such signal is AC square divided by 2 multiplied with the duration. So this is how this ES and AC are related. But now the second question is, how much bandwidth is required in the channel if we want to transmit, M-PSK signal? Because you have to buy the bandwidth here over the channel, so you should know how much bandwidth is occupied by each M-PSK signal. If you know the bandwidth occupied by M-PSK signal, you can accordingly buy the bandwidth of the channel. So in order to find out the bandwidth requirement, we see the power spectral density of the transmitted signal. So this is the, if we plot normalized power spectral density of PSK signal, we are normalizing this by AC square TB. Just remember, AC is the amplitude of this output of output of M-PSK transmitter. So if you do so, this part would be log 2 m and the first null will be 1 upon NTB. And how would you know that the first null will be at 1 upon NTB? For this, you have to just go a bit back and you have to see that in any of the QPSK signal, what we do, we just take n bit at a time and we transmit it through the channel. So since the duration of both I and Q line coder is from 0 to NTB, or sorry, the duration is NTB. And if we choose rectangular pulse, if we transmit rectangular pulse, this is only the shifting. Here we are only shifting. Therefore, if we just transmit this signal, it will be centered around Fc, and the first null will write at 1 upon the duration of this rectangular pulse, which will be 1 upon NTB. Second null will lie at 2 upon NTB, and third will lie at 3 upon NTB. And therefore, this is way simply you can plot the PSD of any M-PSK signal. And the shape will be sync square, because we are choosing rectangular pulse here. Had we chosen other pulse like raised cosine etc., that this shape will change, because I told you that its power spectral density depends upon the Fourier spectrum of the pulse you choose, right, in the line coder. Now the question is, can you plot and compare the bandwidth requirement of the M-PSK scheme? What do I mean by it? I mean, if we increase value of capital M, the bandwidth requirement would decrease or increase. Before going to this, I would just recall you that bandwidth is the separation between the first null to the positive of the Fc and the first null to the left of the Fc. So bandwidth of any M-PSK signal will be 2 times NTB, where N is log 2M. So this is the bandwidth of any M-PSK signal. So for 8 PSK, the power is just, what would be the value of this? Log 2M, that is 3. First null will lie at 1 upon 3 TB, second will lie at 1 upon 2 TB, and third will lie at 1 upon 2 TB. So this is the way we will plot the black. Just look at the black portion of this corresponds to the M is equal to 8 or 8 PSK. And next, just look at the red portion or the red lines. It will corresponds to M is equal to 4 PSK. So this value will be log 2M, that is 2. Log 2 4 is 2, and the first null would lie at 1 upon 2 TB, which is 0.5 TB, and the second null would lie as 2 upon 2 TB, that is equal to 1 upon TB, and therefore the power spectral density would look like this. Thirdly, if we plot the power spectral density of 2 PSK, right, then the power spectral density would look like this, right. In fact, 2 PSK is a one constellation diagram only, so it's not a quadrature, but still we can draw the diagram of 2 PSK, binary PSK or binary PSK, but the formula is same, so you can just plot the power spectral density of binary PSK also. Now you can easily see that bandwidth required, or you can see the formula also, 2 upon log 2M TB, and therefore as M increases, the bandwidth requirement will decrease. So if we transmit higher order PSK signal, the bandwidth requirement will decrease, as you can see by the formula. Just don't see it, we have already written it in the previous slide.